So we're still in the process of finding out which schemes come from varieties of an algebraically closed field K. And we've already identified the pre-varieties in there. And so now we need to have this additional property that distinguishes varieties from pre-varieties, which is that they are separated. And if you recall, we defined being separated as saying that the diagonal inside x cross x is closed. And so ideally, we would now say scheme X is separated if and only if, again, this diagonal inside here is closed. But the problem is then we need to say, what are these spaces? Like, what is X cross X as a scheme? And what is the diagonal inside there? So how to define these products for X and Y schemes? So we could do a naive attempt and take just the Z-periodic product, right? This did work for varieties. So the variety x cross y as a set is just really x cross y. And then we had to be careful what topology we put, what functions we allow, and so on. But at least this worked last time. The problem is the schemes are kind of too big for this to make sense. So to see the problem, note that as varieties, of course, we have that A1 cross A1 is equal to A2. This product here. But then when we go to the scheme level, where we have seen A1 scheme has all the points of the usual A1, and then it has one extra point for the generic point. Similarly for the second factor. So if you take this set product, then what happens is that you get kind of 4 different types of points. You get the nice points that you expect, namely A and B for AB in A2. That's okay. Then you can mix this one here with this on the other factor. So A and the generic point. You have generic point and some B, and you have the product of the 2 generic points. But you see somehow these are, in a certain sense, very few of the points of A2 scheme that we expect, because A2 scheme contains a lot of other stuff. For example, it contains 1 point for the irreducible subvariety vanishing locus of x minus y, some kind of diagonal inside A2. You see, none of these points should give us this thing. So it's just too few points that we get by just a set product. So we need some extra idea. We need to think about this again. And well, less naive attempt. Again, everything in this realm of affine schemes works over the rings. And so if x and y are affine varieties over an algebraically closed field, then we have seen the coordinate ring of x cross y is just the tensor product of the 2 coordinate rings over the field K. So it's again this affine variety, it has this ring. So maybe we should say that the product of spec R and spec S is just a spectrum of such a tensor product. So somehow this has a chance to give us the correct thing for these affine varieties. But one crucial thing, one extra thing that we didn't have to worry about when we work over varieties over K is for a tensor product, you need to specify over which ring you work. That's just how the tensor product works. I mean, somehow the minimal one that you can put is always the integers z, but in many cases, you don't want the integers. So for example, here, we did take the tensor product over this field. So the additional information that we need for these fiber products that we're now working with is that both of the spaces x cross y live over some other space. So here's the definition. So let's say x equals spec R and y equals spec S are both affine schemes over some additional data. So over Z equals spec A. And so somehow these being schemes over Z means there's a morphism from X to Z. And then this morphism of affine schemes corresponds to a ring homomorphism in the other direction. So from A to R, which makes R and S into A algebras. And then we define this affine fiber product of these 2 things over this Z, over this spec A, as being the spectrum of this tensor product, R tensor over AS. So that's the full definition. And then at least we get out of this a nice commutative diagram, actually. Because, well, let's start on the right-hand side. We have R and S are A algebras, so somehow we have morphisms, homomorphisms from A to R, A to S. And then also, I mean, we have this fourth ring R tensor over A with S. And kind of by definition, so somehow this is one of the properties of the tensor product, where we have maps here from R and from S, which just send somehow R to R tensor 1, like this, like this. And then this thing here, exactly the fact that we take the tensor product over A here guarantees us that this here is a commutative diagram of rings. If you translate this, now you take the spectrum everywhere, then you get a commutative diagram of affine schemes. And this taking the spectrum reverses the arrows, so we get somehow arrows in this direction. So somehow the induced map on the schemes from this and this, we can call this pi x and pi y. And we will think of this as being kind of projections to x and y. And this is already looking pretty good. This is reminding us of this kind of universal property of the product of two varieties that we have seen before. Okay. So let's compute this in a couple of cases and see that it gives some reasonable answers. So if x and y are affine varieties over k, so this z is equal to k, then we get their corresponding schemes given by the spectrum of these rings. And then if you take this fiber product, this affine fiber product over spec k, by definition, if we look at the definition, you just take the spectrum of this tensor product. So you just take the spectrum of ax tensor over k with ay. But then from the theory of affine varieties, we know this here is exactly the coordinate ring of x cross y. And then we're back into the situation, we take spec of the coordinate ring of an affine variety. And so this is exactly the scheme associated to this variety. And then looking back, what we have seen is that our definition is compatible with this kind of taking schemes. We can first take a product and then the associated scheme. This is the right-hand side. Or we can first take the associated schemes and then take this fiber product, and we get the same thing. So this is a good sign. And then second, maybe to explain this name, why is it called a fiber product? So we can now do more general things than just taking these fiber products over spec k or the spectrum of a field. So for example, let's take the following two maps. So we have x equals spec k, which is just a point. And this maps to z here, which is the scheme associated to the affine line. And the map on the level of rings is obtained by sending t to 0. And then you should convince yourself this map here is exactly corresponds to the map of varieties, which takes a point and inserts it at 0 in this affine line. This is one thing. And the other one is y is the variety or the scheme associated to A2. And from A2 to A1, you have this map which sends x, y to x times y. On the level of schemes, again, the map in the opposite direction takes this coordinate function t on z and sends it to x times y, exactly what gives you the map of varieties. And so we have these two morphisms, and kind of the diagram looks like you have here on the right-hand side, you have this family of these vanishing loci of x times y equals t. As t varies, you get different preimages or different fibers. And then you want to take the fiber product with the inclusion of this point inside the affine line. And then what turns out happens is that you exactly get the fiber of this map over this point. So the preimage will exactly be the scheme associated to this coordinate cross. So let's see this on the level of rings. So by definition, x cross z over y is, well, you just take the tensor product. So here you have k, k of t and k of xy, and they form this tensor product. And then now how to calculate this tensor product? Well, we have to use a result from commutative algebra. And what we can do is we can see this k here as k of t modulo t. And this way we explicitly identify it as an algebra over k of t. And then there is a lemma here from commutative algebra, which says, if you have a ring homomorphism and an ideal in the domain, and then you look at such a tensor product, so you have R modulo J tensor over R with S, then there's an isomorphism of this with S modulo the ideal generated by phi of J. Okay, so that's just something that you can show in a few lines. And so here in this situation, we're exactly in this case. So somehow R is this K of T. It maps to, via this map here, it maps to this S, this thing here. And we and we take the tensor product with something of this form, the ring modulo an ideal. And so the lemma tells us, okay, we can calculate this. We just get this S here modulo the ideal generated by the image of this ideal, so the image of the ideal T under this map here. Okay, we have to let this sink in. And well, the image of T under this thing is the ideal generated by X times Y. And so we exactly get this thing here. And then we see this spectrum here is exactly the scheme associated to this usual vanishing set. So I recommend to go through this calculation again in detail to convince yourself of this. But this tells you this this fiber product is not just a way to, well, take some product of schemes, but in fact, it can give you more than we had originally seen for the affine varieties, because it can, for example, allow you to extract for such a morphism here from Y to Z, to extract a fiber of this morphism here as a scheme. And so that can be very useful. Okay, so these were just some examples of affine fiber products. And now we want to go beyond this affine situation. We want to take fiber products of arbitrary schemes. And so this is the following construction. And this construction is very parallel to the construction of the product of affine varieties and the product of then varieties that we have seen when we defined what it meant to be separated there. Okay, so the construction of the fiber product, we start with X, Y, and not just abstract schemes, but they both live over the same base scheme Z. So here, this is this part of this diagram. And then a fiber product. So this is the input. You have two things over the same space. And then a fiber product of X and Y over Z is a tuple, first of all, of a scheme P, and then morphisms from P to X and Y. And these are kind of the projections to the two factors. And you want to have a universal property. And so the universal property is almost the same as we had for varieties. So it says that for any scheme W and morphisms W from X to X and to Y. So for the scheme level, we would just say for any morphism here and here, we find the unique morphism to P. But now we work over this extra scheme Z. And so with the additional property that we like is that this whole diagram should commute. So in other words, if you go from W to X and then to Z, it should be the same map as if we go from W to Y and then to Z. These should be the same morphisms. So if we have this commuting property, then we find the unique morphisms of schemes from W to this product P, such that this entire diagram commutes, so that HX and HY are given by the composition with these projections. Okay, so that is again this universal property, and it's very close to the property that we had for the product, which I mean essentially just said giving a map to the product is the same as giving a map to the first vector and the map to the second vector. The only difference that we now have is that we need to add comma, which commute with the map to Z. Okay. So this is an abstract definition. We say a fiber product of X and Y over Z is this. And then, as before, there's a follow-up proposition which just says existence and uniqueness. So the first part is that if all of these involved schemes are affine schemes, then the thing that we defined before this X cross ZY is a fiber product, the spectrum of the tensor product. And part B is then if X, Y, and Z are arbitrary schemes, then this fiber product P exists, and it is unique up to isomorphism. So since we don't use this fiber product so much in the future, let me just give a proof sketch and let me just go through it like this. So for the first part, if everything is affine, then we're in good shape because then we can translate everything to the realm of rings. So so if all of these spaces are affine, so again we have this kind of R being an A algebra, S being an A algebra, and then we claim that we can, we copy this diagram from above, this we can fill in. And then the condition here in this thing that we have maps from W to X, W to Y, such that the map downstairs to Z commutes. This property is just saying, well, on the level of rings, we have maps in the opposite direction here and here, such that the maps from A commute like this. But then if we restate this outer diagram here, this outer diagram is saying that we have two A algebras, R and S, and then via these maps, they both map to B, and well, A also maps to B by these two different paths, and this is the same. So in other words, we have these two A algebras, and they have maps to this, which then also becomes an A algebra. And then the universal property of the tensor product says, in this situation, there is a unique ring map, or there is a unique map of A algebras, in fact, from R tensor A of S to B, like this. We call this phi tensor psi, such that this entire diagram here commutes. And so this universal property of the tensor product then tells you that exactly there is a universal, or there is then a map of affine schemes from spec B to spec of this thing here, which is the fiber product, such that everything commutes. Okay, so when everything is affine, it just follows from commutative algebra. And then if W is an arbitrary scheme, then what you just do is you cover this with the scheme spec BI. So you find here for this W, you find a cover by different spectra, and then by this already proven case, you get a lot of morphisms from the spec BI to this spec R tensor AS, and all of these affine patches, because of essentially again because of this uniqueness property, all of them must glue on their overlaps. And so they glue back together to a morphism from W to this fiber product. And then this is exactly what he wanted to construct. That given this outer diagram, you find this morphism here. Okay. So this shows that on the level of affine schemes, we really do the right thing here. And then finally, when X, Y, and Z are all arbitrary, and we want to show existence and uniqueness of this fiber product. And then what you just do, we know what to do in the affine case. So somehow you choose compatible affine covers of everything. And so if you do this, you will see you first choose an affine cover of Z. Then on the preimage of everything, you choose affine covers of X, Y. And then once this is done, you know what parts of P you should get. P should also be covered by the affine fiber products. And then you just have to show that this thing which you constructed has this property here. And again, so somehow if you then have W mapping here and here, you get compatible affine covers on W, and then everything must glue. So somehow, yeah, so you glue these affine fiber products, you get a candidate for this product, and then you just check that this has the correct property. This is the uniqueness part, and sorry, it has the unique property. This is the existence part, and that uniqueness is satisfied. And so we went through this kind of proof already in detail in this video 0505. And this was the proof of this proposition 515. And there we did give all the details. And you will find that basically a lot of the proof is just exactly the same, which you can now do in this language of affine schemes. Okay, so this is the idea. We defined what we mean by fiber product, and now it exists and is unique. And so somehow we can denote this P by X cross Z with Y for X, Y, and Z schemes. And then just a few corollaries at the end of the video. So what this now also allows us is to do some scheme theoretic intersections for arbitrary schemes. You have already seen what the intersection of two affine subschemes is. And now, so whenever you have two closed subschemes, x1 in Y and x2 in Y, like this, then you define their intersection as just take this fiber product over Y, because these are now two schemes over Y, so you can take the fiber product. And then this has kind of two different, a priori different maps to Y, but these two maps coincide, because somehow this is the statement that if you take this fiber product here, then you have two maps to this base space, and they should both be the same. And so in this way, I mean, you can see this as closed subscheme in Y, and then if you take the intersection, it's again a closed subscheme in Y. And it does the correct thing when everything is affine. So somehow, if you have an open subscheme U inside Y, then by definition of these being closed subschemes, we know that these premises of U are given by this spec R modulo J1 and spec R modulo J2, where J1 and J2 are the ideals cutting out X1 and X2. And then if you go through the definition that we just gave, because now it's an affine fiber product, so this preimage here in the affine fiber product, it's just given by the spectrum of this, or somehow it's first of all given by this fiber product here. And then by definition of the affine fiber product, you take this tensor product here, R modulo J1 and R modulo J2 over R. And now this kind of thing we have seen before, so you can apply the same lemma that we had above. Let's look at it again. So here, for such a tensor product, you see what you just do is you take the ideal, for example, on the left-hand side and take the image in this right-hand side. And this is what you need to quotient out by. And if you apply this here, then you see this tensor product here is exactly the same as taking this R modulo J2, for example, and then additionally modding out the image of J1. And that's exactly the same thing as taking this, just the sum of these ideals and modding this out. Somehow this is spec R modulo J1 plus J2. And this is exactly how we defined previously, kind of defined by hand, what the scheme theoretic intersection of these two things is, that you take the sum of the ideals, and this is what cuts it out. And so we see now with this more general definition of fiber products, we can recover this old definition of the scheme theoretic intersection. So that's always a good sign if your new theory kind of in retrospect predicts the old theory. Okay. So this was everything about fiber products, and then in the final part of the chapter, we can define what it means for a scheme to be separated, and then we can identify varieties inside this category of schemes.